In this module, we will identify the hydraulic system components in the Fokker 100 and examine the layout of the hydraulic system. In addition, we shall identify the subsystems that require hydraulic power and discuss hydraulic subsystem supply. In the description section of this module, we shall locate and identify hydraulic system controls and indicators in the flight deck, and discuss normal fluid pressure in the hydraulic system. Hydraulic system non-normals, together with annunciations at the flight deck, are discussed in the Malfunctions section of this module. The supply of hydraulic power to aircraft subsystems in the Fokker 100 comes from two independent hydraulic systems. These systems are identical in performance, but differ in capacity. Hydraulic System 1 has a reservoir capacity of 23 litres, and System 2 has a capacity of 4 litres. In addition to the separate reservoir supplies, each system comprises 2 engine-driven pumps, each equipped with fire shut-off valves, a low-capacity electric-driven pump used mainly for maintenance purposes, and a system accumulator. In addition, both Hydraulic System 1 and Hydraulic System 2 include check valves to prevent reverse flow, and sensors and transmitters to relay data and alerts for display at the hydraulic panel located in the flight deck overhead panel. Hydraulic System 1 and 2 incorporate high-pressure filters downstream of the engine-driven pumps, and low-pressure filters on the subsystem return flow lines. These filters remove debris and contaminants from the hydraulic fluid. Bleed air pressure is regulated to provide a positive hydraulic fluid pressure of 40 psi at the engine-driven pumps and to prevent aeration of the hydraulic system. Downline of the hydraulic system accumulators, hydraulic fluid moves into the main supply lines, providing hydraulic power to actuate the various subsystems. Hydraulic fluid return flow is via filtered lines or bypass lines to the hydraulic reservoirs. System 1 and System 2 are the same in design and operation. They differ in fluid capacity and in the consumers they serve. System 1 supplies hydraulic power to the left-hand aileron, the rudder, the elevator, the horizontal stabilizer, speed brakes, thrust reversers, landing gear, nose wheel steering, alternate braking system, flaps, and lift dampers. System 2 supplies hydraulic power to the right-hand aileron, rudder, elevator, stabilizer, and the normal braking system. Hydraulic fluid pressurized to 3000 psi provides hydraulic power to actuate the subsystem consumers. To ensure continued operation of aircraft primary flight controls, System 1 contains a priority valve located upstream of the landing gear, nose wheel steering, lift damper, alternate brakes, and the flap subsystems. If hydraulic pressure falls below 2,300 psi, the priority valve closes. Hydraulic power from System 1 is available for the flight controls, speed brake, and thrust reversers.
The priority valve will reopen when the hydraulic pressure rises above 2,650 psi, restoring hydraulic power to all System 1 consumers.
Controls and indicators for the hydraulic system are located on the hydraulic panel in the flight deck overhead panel. Sensors at the hydraulic reservoirs measure fluid levels. These levels are displayed at the hydraulic panel as a percentage of total tank capacity. The sensors at the hydraulic reservoirs detect low hydraulic fluid quantity and illuminate the amber low quantity light on the hydraulic panel. For System 1, low quantity is enunciated if the reservoir is below 35% tank capacity. And for System 2, low quantity is enunciated if the reservoir is below 20% tank capacity.
Fluid overheat alerts are displayed separately at the overhead panel for System 1 and System 2. An overheat is enunciated if fluid temperature in a reservoir exceeds 90 degrees centigrade. Overheat and low quantity alerts are also indicated at the MFDS.
Bleed air pressure utilized to provide positive fluid flow is also monitored in each hydraulic system. Low tank pressure is enunciated at the MFDU. The normal operating pressure of both hydraulic systems is 3000 psi. Sensors at the pump outputs measure system pressure, which is then displayed at the hydraulic panel. Low pressure conditions are enunciated by local lights in the associated engine pump push button at the overhead panel and at the MFDU. And check valves located at pump outputs prevent reverse flow of hydraulic fluid.
Only System 2 has a small capacity accumulator upline of the system consumers, the hydraulic accumulator.
Smooth out shock loads within the hydraulic system and provide an emergency source of hydraulic power.
The System 2 accumulator is charged with nitrogen to 1000 psi.
In addition to the engine-driven pumps, each system has an electrically driven pump used mainly by maintenance for system tests. The electric pumps are switched on and off from the hydraulic panel. The capacity of the electric pumps is insufficient to meet the demands of either hydraulic system. The pumps can, however, be used to pressurize the braking system prior to engine start. High and low pressure filters are fitted in both hydraulic systems. These filters are equipped with pressure differential switches. In the event of a filter blockage, the associated pressure differential switch operates. There is no indication that the flight deck and system operation is unaffected. The operation of the hydraulic system on the Fokker 100 is fully automatic. Provided both System 1 pumps are operative and at least one System 2 pump is operative, the hydraulic system is now prepared for flight. In this section, we will examine hydraulic system malfunctions, discuss how malfunctions are enunciated, and the compensatory action required during approach and landing. An engine pump fault in either system will not affect the operational status of the system. The remaining system pump is capable of meeting all hydraulic power demands for that system. An engine pump fault generates a Level 1 alert with local light and a single chime. The Alert Hydraulic System 1 Engine 1 pump is enunciated at the primary page of the MFDU, and the procedure, pump off, at the secondary page of the MFDU. Please cancel the local alert before continuing. The local light switches to off, indicating that the associated pump is not operating. Note that hydraulic fluid remains in the inoperative pump for cooling and lubrication purposes, and that no status messages at the MFDU are generated for this alert. Engine pump fault alerts are inhibited during certain flight phases, as detailed in the alert diagram. If a low tank air pressure fault is detected, a Level 1 fault is generated by the FWS. No local lights will illuminate for this alert, but hydraulic tank pressure will enunciate at the primary page of the MFDU. System operation remains unaffected and no crew action is required. Note that cavitation should not occur if the air pressure fails after the pumps have been operating. There is, however, the slight possibility that large system pressure fluctuations may occur during periods of heavy system loading. Low hydraulic tank air pressure alerts are inhibited by the FWS during certain flight phases. The effects of a single hydraulic system failure depend on the failed system, since System 1 and System 2 power different subsystems. A complete System 1 failure causes a loss of hydraulic power to the left aileron, speed brake, thrust reversers, landing gear, nose wheel steering, alternate braking system, flaps, and the lift dampers. Rudder, elevator, and stabilizer will also have one actuator affected. A complete System 2 failure results in a loss of hydraulic power to the right-hand aileron and the normal braking system, and one actuator in the elevator, rudder, and stabilizer. A complete hydraulic system failure requires manual and alternate system operation. We will discuss total hydraulic system failure at the end of this section. The hydraulic systems are normally pressurized to 3000 psi. If pressure drops to 2400 psi or less, a low pressure alert will be generated by the FWS. Low pressure in hydraulic system 1 causes the alert Hydraulic System 1 low pressure to be displayed at the MFDU primary page and the associated procedure to be presented at the secondary page. The relevant engine pump push buttons illuminate faults at the hydraulic panel. Low pressure in hydraulic system 1 or 2 is a level 2 alert, causing the master caution lights to flash and a double chime to sound. Please cancel the level 2 alert before progressing. After cancelling the master caution lights, check the procedure displayed at the MFDU. Now switch off System 1 engine 1 pump and engine 2 pump.
Switch off System 1, Engine 1 and 2 pumps.
Hydraulic System 1 is now inoperative.
With Hydraulic System 1 inoperative, the status page details that flight controls are on single channel and the following systems are inoperative: normal gear, normal flaps, the speed brake, reversers, and nose wheel steering.
The Hydraulic System 1 fail procedure requires that flaps are extended by means of the alternate flap procedure and that landing gear is lowered by following the alternate landing gear procedure. These procedures will be discussed in more detail in the appropriate modules. During single-channel operation of the flight controls, aileron forces are approximately double. If the speed brake was extended when the failure occurred, it can be retracted, though at a slower rate than normal. When landing with a Hydraulic System 1 failure, complete the System 1 low-pressure procedure and establish the landing configuration early. Select the landing gear and flaps via the alternate systems. Use flaps 25 for landing if runway length permits. With no Hydraulic System 1, the thrust reversers are inoperative. Select idle reverse to ensure lift damper extension after landing. Nose wheel steering is also inoperative. Pilots should be prepared to use asymmetric braking for directional control. Clear the runway, but do not taxi. Note that in go-around, the landing gear cannot be retracted, and the flaps must be operated via the alternate system. Enunciations and procedures for a Hydraulic System 2 low-pressure condition are similar to those we have already examined for a System 1 low pressure. Hydraulic System 2 low pressure causes a Level 2 alert, together with a message at the MFDU primary page and the associated procedure at the secondary page. The System 2 pressure indicator displays a low pressure value, and the System 2 engine pump push buttons display fault lights. Now follow the procedure to shut down hydraulic system 2. Hydraulic system 2 is now inoperative. The status page details that the flight controls are now on single-channel operation. During single-channel operation of the flight controls, aileron forces are approximately double. Normal brakes are inoperative when hydraulic system 2 fails, but the alternate brakes, including skid control, become available automatically. Either System 1 or System 2 low-pressure alerts are inhibited by the flight warning system during certain flight phases. A hydraulic System 1 low quantity causes a Level 2 alert when reservoir quantity falls to approximately 35% of capacity. The quantity indicator at the hydraulic panel displays percentage of reservoir capacity remaining, and the amber low quantity light illuminates. The amber master caution lights at the glare shield panel flash and a double chime sounds. The left MFDU displays the alert Hydraulic System 1 low quantity, and the associated procedure appears on the right MFDU. After cancelling the master caution lights, follow the procedure displayed at the MFDU by switching off System 1 engine pumps 1 and 2.
Switch off System 1, Engine 1 and 2 pumps.
Hydraulic System 1 is now inoperative. With Hydraulic System 1 inoperative, the right MFDU status page displays the affected systems. The flight controls operate on single channel with aileron forces doubled. Normal flaps, normal gear, speed brake, reversers, and nose wheel steering are all inoperative. The Hydraulic System 1 fail procedure, as applied following a Hydraulic System 1 low pressure, is also to be applied following a Hydraulic System 1 low quantity. Alternate flap procedure and alternate landing gear procedure should be carried out, and the speed brake can be selected in if extended at the time of the hydraulic failure. You will recall that the retraction time for the speed brake will be longer than normal. A Hydraulic System 2 low quantity causes a Level 2 alert when reservoir quantity falls to approximately 20% of capacity. The quantity indicator at the hydraulic panel displays the percentage of reservoir capacity remaining, and the amber low quantity light illuminates. The amber master caution lights at the glare shield panel flash and a double chime sounds. The left MFDU displays the alert Hydraulic System 2 low quantity, and the associated procedure appears on the right MFDU. Now follow the procedure to shut down Hydraulic System 2. Hydraulic System 2 is now inoperative. The amber master caution lights at the glare shield panel flash and a double chime sounds. Flight controls operate on single channel and aileron control forces are doubled. Normal brakes are inoperative, but alternate brakes become available automatically. Low fluid quantity alerts are inhibited by the FWS during certain flight phases. The alert inhibition is identical for System 1 and System 2 low quantity. In the event of a hydraulic system fluid overheat in Systems 1 or 2, a Level 2 alert is generated. For an overheat in System 1, the message Hydraulic System 1 Overheat will appear at the primary page of the MFDU. The procedure for this alert is given at the secondary page of the MFDU, and the local annunciator Overheat illuminates at the hydraulic panel. The procedure for both System 1 and System 2 overheats requires that the affected system engine pumps are selected off at the hydraulic panel. Switching off a system due to overheat leaves the associated subsystems inoperative. In this example, only those subsystems powered by System 2 remain operative. Prior to approach, an MFDU displayed message informs the flight crew to select the affected system pumps on. The overheated hydraulic system should be switched on again, allowing full hydraulic actuation of all hydraulic subsystems. Alerts for hydraulic system overheats are inhibited by the flight warning system during certain flight phases. A total hydraulic system failure, where both systems 1 and 2 become inoperative, results from low pressure in both systems, low fluid quantity in both systems, low pump pressure in all engine pumps, or fluid overheat in both systems. A combination of these faults may also result in a total hydraulic system failure. A complete hydraulic failure causes a Level 2 alert and a hydraulic system 1 and 2 low pressure alert at the left MFDU. The associated procedure, together with speed limitations and the message to avoid areas of turbulence, appear on the right MFDU. Local fault lights appear in all system engine pump push buttons. Follow the procedure on the MFDU and select these pumps off. Hydraulic systems 1 and 2 are now inoperative. The status page displays that the flight controls are on manual and that normal flaps, normal gear, speed brake, thrust reversers, nose wheel steering and the yaw damper are inoperative. In the event of a total hydraulic system failure, only the manual and alternate systems are operational. With flight controls in manual, elevator load feel increases. Stabilizer control is possible with the alternate stabilizer control on the pedestal. Slow stabilizer response should be anticipated, and large out-of-trim conditions should be avoided. Aileron control forces are approximately doubled in manual control. Turn coordination and yaw damper are not available. Reduced rudder control, requiring high pedal forces, is available at landing speed, and crosswind should be restricted to 10 knots. The speed brake can be selected in, if extended, at the time of hydraulic failure. When landing with a total hydraulic system failure, ensure that the hydraulic system 1 and 2 low pressure procedure has been completed. Restrict the crosswind to a maximum of 10 knots, and establish landing configuration early. Select the landing gear down and flap extension via the alternate systems. Use flaps at 25 if the runway length permits, and be aware that the thrust reversers are inoperative. Use the auto throttle system if available. If the auto throttle system is not available, the pilot not flying may control thrust levers during final approach and landing. Select idle reverse to ensure manual lift dumper extension after landing. Normal brakes are inoperative following a total hydraulic system failure. Alternate brakes are available utilizing hydraulic power from the System 1 accumulator. Apply brakes and maintain pressure until taxi speed has been reached. Avoid activating the anti-skid system and monitor the alternate brake system pressure. Nose wheel steering is inoperative. Use asymmetric braking for directional control. Clear the runway, but do not taxi to the gate. If a go-around is performed with a total hydraulic system failure, the landing gear cannot be retracted. Flaps must be operated via the alternate systems. During certain flight phases, alerts for the total hydraulic system failure are inhibited by the flight warning system. Each hydraulic system incorporates a fire shut-off valve that prevents hydraulic fluid flow into the engine pumps in the event of an engine fire. If a fire handle is pulled, the associated dual fire shut-off valves close and terminate the flow of hydraulic fluid to the affected engine pumps. Hydraulic system operation remains unaffected. One pump per system operates from the remaining engine, providing sufficient hydraulic power to supply all System 1 and 2 consumers. In this module, we have seen that the hydraulic system comprises hydraulic system 1 and 2, and that these systems jointly power primary flight control subsystems. We have examined the hydraulic system controls and indicators at the hydraulic panel, seen that normal operating pressure for each system is 3000 psi, and discussed reservoir capacity. We have discussed the alerts generated by the FWS in the event of low system pressure, low fluid quantity, and fluid overheat, how these alerts are enunciated at the MFDUs and local lights at the hydraulic panel, and seen when these alerts are inhibited. Landing procedures in the event of a System 1, System 2, or total system failure have been illustrated. Further discussion of alternate landing gear operation and alternate flap operation can be found in the relevant modules. In conclusion, the following chart summarizes the subsystems affected by hydraulic system failures and details actions required.